Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello, let us continue our discussion on this plastic deformation. In the last class, we looked at what are all the fundamental issues with regard to yield criterion or fracture criterion and so on. We looked at two important yield criterion, though there are different yield criterions are proposed. The popular ones are the Tresca yield criterion, that is also called maximum shear stress criterion. The other one is called von Mises or distortion energy criterion. It is also called octahedral maximum shear stress criterion, so on. And then we also looked at the maximum principal normal stress fracture criterion, which is mostly suitable for brittle materials. On the other hand, these two other criterions suitable for ductile materials. At the end, we also looked at the criterion, which is these criterions, how they are modified. In the case of semicrystalline or polymeric materials or long molecular chain materials, incorporating this pressure effect, how these expressions are modified, and some new empirical models were proposed, and this is what we have seen. So now we will move on to the deformation behavior itself, and the first topic we are going to address is deformation mechanisms of single crystals, and then we look at the what are all the aspects which describe the deformation mechanisms in a single crystal. Then we will move on to polycrystal deformations. So if you look at what are the primary mechanisms which governs the deformation is first is slip and the rest straining. We will first see what is slip. Slip in a crystallographic terms, when you describe it, the slipping of a large portion of crystal aggregate. So that is a slip, normal slip. And the slip is described by a term called slip system. Now, okay, what is slip system? Slip system consists of two quantities. One is slip plane, a plane allowing the easiest slippage, okay, in a very simple term. Wide interplanar spacings and highest planar densities. These are all the very important requirements of for the easy slip that has to take place. Okay. And then a slip direction of the movement, highest linear density. So a slip system consists of a slip plane and a slip direction, and these are all the attributes. Now let us look at the example of highest dense plane and so on. For example, here we have taken the face-centered cubic crystal unit cell, and what you are seeing here is the 111 plane, which is also we have just seen in the previous lecture called octahedral plane, and this plane has the highest planar density in an FCC system. And what you are seeing in that pink color arrows indicating the direction. You have a three direction which can be easily identified from this. And if you take out this plane and then put it in a planar view, and this is how it looks like this. So there are A, B, and then C type of atoms, and then they're all stacked one on the other. And in the planar view, from the top view, I would say from this corner, if you see, it will all look like this: A, B, C. Okay. So FCC slip occurs on 111 planes. That is, you see that 111 is denoted by a flower bracket. That means it's a family of planes. There are also close packed planes in 110 direction. This is also a family of directions. It's also called close packed direction. There are about 12 slip systems in face-centered cubic lattice or face-centered cubic crystal, and then we'll see how dislocation proceeds. Dislocations proceeds because of the two aspects. First is because we are applying a load, which is measured as stress, and because of that the dislocation moves in the crystal. That is the primary action that results in the deformation. So this is a schematic which shows where we apply the tensile force is F, and the cylindrical member is getting slipped, and the slipped area you can see that, and this is a slip direction, and applied tensile stress is sigma is equal to F by A, force by unit area. And we know that crystals slip due to a resolved shear stress, tau R, resolved shear stress. So this we have already know that a total stress or normal stress can be resolved into shear stress and normal stress. Okay, a total stress can be resolved into normal stress and shear stress. So slip, the shear causes by the resolved shear stress component of the stress, applied stress. So applied tension can produce such a stress, and the resolved shear stress is tau R is equal to the shear force divided by the area where the shear force is acting, which will give the resolved shear stress. And if you look at this schematic, and it clearly depicts that the area which is subjected to the shear force as well as the plane on which the shear force is acting. So, and then you see this NS is a slip plane normal, just to give the illustration clearly between this applied tensile stress versus resolved shear stress. And then if you look at the relation between sigma and tau R, we can just further expand this tau R is equal to Fs by As. If you look at what is Fs and what is As, and then for that I need to bring a more schematic here. This is the cylindrical member which is subjected to slip, and then it's a slip plane, and then this slip direction, and the force is tensile force, uniaxial force, and the area of the cylinder is A here, and this is the green line is normal to the slip plane, which is kept at an angle 45 degree here, and the angle between the slip plane normal to the tensile axis is phi, and the angle between the slip direction and the tensile force is lambda. So now coming back to this the relation between sigma and tau R, and tau R is equal to Fs, that is shear force divided by the area of the plane where the shear force is experienced. So Fs is F times cos lambda. That means the component, the stress component which is contributing to this force in this lambda, that is in this direction, the force which is perpendicular to this, and then the component which contributes to this slip plane is F cos lambda. Similarly, the area, this is A, this is A perpendicular. This is the A, which is where we see that the force is perpendicular to this plane. But then the area which is actually subjected to the shear force is given by A divided by cos phi because of this angular relationship. So if you look at this substitutions, then what you will see here is tau r is equal to sigma cos lambda cos phi. So that is the kind of relation you get for the sigma and tau r. So this is a fundamental requirement for the slip to takes place. Okay. So this is it is not that the resolved shear stress of any quantity will cause slip. There is something called critical resolved shear stress. That means it is a kind of a condition for dislocation motion. If you recall, we have also seen that a stress required to move a dislocation. So Pearl's-Nabarro equation, if you recall, it is something similar to that. You can relate that. Of course, there it is assumed that the crystal is free of any other dislocation, just one dislocation in a perfect crystal, right? That's quite. But here we are talking about a bulk. Initial condition could be of any kind, but here also it is a single crystal. The condition for dislocation motion, the TR should be greater than tau r, not TR. Tau r should be greater than tau CRSS. So it should be greater than, the resolved shear stress should be greater than critical resolved shear stress that is required to move the dislocation. That is how you should look at it. So the critical resolved shear stress values are typically of 10 to the power minus 4 GPa to 10 to the power minus 2 GPa. The crystal orientation can make it easy or hard to move a dislocation. Okay, this is very important. We will look at the details as we move along. And the tau r is equal to sigma cos lambda cos phi. So that clearly shows that the orientation is very important, and we will show this by some schematic to explicitly arrive at the condition of a slip. So here you see that this the rectangular member is subjected to a tensile force, and then suppose if you assume that the lambda is 90 degree, and then what happens to the critical resolved shear stress? Then it is 0, because lambda will become 0 here. I mean, lambda is equal to, lambda if it is 90, then this component will become 0, and then entire tau r will become 0. On the other hand, if you take lambda and phi is 45 degree, then it gives a value tau r is equal to sigma by 2. Okay. On the other hand, if you make phi is equal to 90 degree, then also tau r becomes 0. So what it means is the tau maximum at lambda and phi is equal to 45 degree. Okay. So this is one simple substitution which illustrates the maximum resolved shear stress is obtained at the angle of 45. This we have already seen in the yield criterion. Even before that, the shear stress plane and all that we have seen several times. The maximum tau max is occurring at 45. So if you look at the plastic flow in a single crystal, so this is how the crystal will slip, and then we can look at the slip lines. The slip plane will appear like this against this shear force direction, and each one will have the slip planes need not be uniform like this. It could be randomly. I would say that it's a random aggregates of the slip plane will appear at, with the non-uniform distance between them. So this is just a schematic which I am trying to show. So this is how the slip plane will look like, and the other hand, the other mechanisms, twin, will look like this. And we will see the details in few minutes. But what you see is here is this is a untwinned plane, and this is a twin planes, and then in between you have the twinned region, and these are the shear stress directions. And this is a single crystal metallic sample, which you can see that the real-time experiment which is given in this text. I just brought to give an example how the slip range is exactly looking like what we have just shown in this schematic, the real-time slip, slip regions will exactly look like this. Sorry. So now we'll go a little more into the slip system. Each crystal has a number of characteristic slip systems. So very important. We are talking about different type of crystal systems. So each crystal system has got a characteristic slip systems. For example, FCC we have already seen a slip takes place in 111 type of octahedral planes and one bar 10 direction. And we have 4 type of 111 planes and 3 110 directions, so which is shown here in this schematic, and 4 into 3 is a 12 slip systems. Okay, so you have examples: copper, nickel, aluminum, lead, gold, silver, gamma, iron, so on. They all belong to these kind of crystal systems. And if you go to BCC crystal, that is body centered crystal lattice, so you have 110 plane and 111 direction of this one. This type of slip system is displayed by alpha iron, tungsten, molybdenum, beta brass. So they have got about 12 systems, and there are other system. 211 is a plane and 111 is direction. This slip system is also readily active in alpha iron, molybdenum, tungsten, and sodium. So this again contributes to another 12 slip system. And the third slip system which exhibits, which the BCC exhibits, is 321 planes and 111 direction, which is giving rise to about 24 system like alpha iron and potassium. So all these directions are marked here for the rough pick reference. So if you look at the number of slip systems as compared to FCC, they are more. Okay, but the problem is BCC crystals are not close packed. The slip predominantly occurs in 110 planes that has the highest atomic density. Okay, so you have to remember that. Similarly, if you look at the slip systems in hexagonal close packed crystal, and the primary slip systems are the basal plane. So this, you can see that this is a basal plane, and the directions are given here, 3 directions: 0, 0, 0, 1 basal plane, and 1, 1, 2 bar 0 with 3 directions. So 1 into 3, 3. Examples of this kind of slip system exists in cadmium, zinc, magnesium, titanium, beryllium. And another type of slip system, 10 bar 10 slip planes, and this is called prism plane, and 112 bar 0 direction. You have 3 planes like this, and then 1 direction, so 3 slip systems. Titanium, magnesium, they also show pyramidal planes. You can see that pyramidal planes, which is shown here. This is pyramidal planes, and the same direction. So you have 6 pyramidal planes of similar direction. So 6 systems. So you see again in HCP about 12 slip systems. But the problem with the HCP is it is very sensitive to the C by A ratio. If HCP crystals have high C by A ratio, slip occurs along basal planes, that is 0, 0, 0, 1 type of planes. For crystals with low C by A ratio, slip also occurs in this type of prism planes. Okay, so this is one thing we have to remember. So you see that compared to FCC, both BCC and FCC do not have a high dense planes. Okay, that's bottom line. So if you look at a little more detail about this plastic flow in single crystals, so we have seen that the plastic flow initiates when tau CRSS reaches some critical value characteristic of the material. Okay, so the stress is designated tau CRSS and is related to the tensile yield stress sigma through this relation. That is sigma y is equal to m times tau CRSS. Okay, so this is also known as the Schmidt law. So the CRSS, tau CRSS is the invariant for a given material. Okay, so the value of tau CRSS depends on test conditions such as temperature and strain rate, as well as the structural features such as material's initial dislocation density and purity. So here is an important plot that we need to keep in mind when we, with regards to the critical resolved shear stress is concerned. So the critical resolved shear stress is plotted here against the temperature, tau CRSS versus T plot. You can see that it's not only showing the temperature variable, there is also a strain rate variable. Okay, the dashed line is epsilon 1 dot, which is greater than epsilon 2 dot. Okay, so the solid line is epsilon 2 dot. That is okay. So so it shows both effects, temperature effect as well as strain rate effect. So what does it show? It's very interesting actually. You can see that this plot exhibits almost 3 regions, the region 1, region 2 and region 3. Okay, and then what are the critical points to be noted? What are the critical points? In region 3, what is that we are seeing? The T is less than or equal to 0.7 Tm. Tau CRSS decreases rapidly with the increasing temperature. Okay, so you can see that in region 3, the tau CRSS decreases rapidly with increasing the temperature. Okay, it also function of strain rate. The strain rate is also a function of strain rate. So that means in both strain rates they look different. So that means it is sensitive to strain rate as well. If you compare the region 1, where the temperature is greater than or equal to 0.25 Tm, the tau CRSS is function of temperature and strain rate. We can rewrite this tau CRSS equal to tau A plus tau star. What is this tau A? Where the tau A is the thermal component of the stress and tau star is the thermally dependent term. Very important. Okay, so you have a temperature dependent term and a thermal component, temperature independent term. Okay, the tau CRSS has got 2 terms, tau A and tau star. Okay. In effect, tau star approaches 0 at the temperature marking the transition from region 1 to 2. This is true because the moment it reaches this plateau, then it starts the region 2 till the end, it is 0. The temperature dependent component tau star is 0 in the region 2.